All right, the other topic we need to look at is resonance structures. And it just says it right here. Sometimes a single Lewis structure does not provide an adequate picture because there's more going on. So the one that is shown here is O3. If I do it in a written out Lewis structure from scratch, this is kind of what it would look like. So I'd have O3 here, and you'd have oxygen. Don't worry about the shape, if it's bent or if it's not. You have 3 oxygens, okay? And if you count up all the elements or the electrons that you need 18 electrons because they each would be 6. So when it's all said and done, basically what happens with this is that you have an uneven distribution of electrons, right? So in this case, I have not enough electrons, so this is positive, and here I have too many, so that formal charge is negative. Why does it have to be that way? Why couldn't it be like this? And it could, and that's the whole point. And because of that, this now would have a positive charge still, but this now would have the negative, right? And we could add all the dots in there, but that's the whole point of a resonance structure. So it's really important for you to understand, oh, there's a typo here. This should be negative 1.5, not 1.2. And all it is saying is it's not a full, the bond has a character not of a single bond, not of a double bond. So it's got a bond character of basically 1.5 bond. So the real molecule, though, is not a single bond and then a double bond, or a double bond and then a single bond. It's more of a hybrid. It has a little bit of both. So it's kind of like 1.5. It's not single and double. It's always single and it's always double. So it's more of a 1.5 bond, okay? So let's just jump right down into what we need to talk about today. Resonance recognition, okay? This is the important part. Atoms must be connected in exactly the same way. So if you look at my structure, the atoms didn't move. I have a double bond and a single bond, or a single bond and a double bond, right? It's all the same. Well, that's still very, very important. Resonance forms differ only in the placement of electrons. So it's really, I know it's in a box, but the key for resonance structures, electrons move, but atoms do not. If atoms move, you don't have a resonance structure. Okay? So there's a term called delocalization, and that's what allows for those electrons to move around. So the charge or the electron cloud is able to kind of be a little more free. It's not localized, it's delocalized. So the point of this, and this is so important for us moving forward, is that when you find that something is a resonance, it's actually more stable. Because then it's not just, let's look back at our example, I don't have a single then a double or a double then a single, I kind of have both. So it's actually stronger. So when we start doing compounds where making decisions about what is reacting and what isn't, what should react, what shouldn't, it's actually going to go off of that idea of stability. So I can't emphasize that enough, that if you have more bonds, this is a priority rule, the more bonds you have, it's usually about stability. So bonds being equal, consider electronegativity. Negative charge is better with something that's more electronegative atom. So if you look at the periodic table, we have our normal elements that we're dealing with in organic chemistry, and they go from left to right as carbon, nitrogen, oxygen, fluorine, if you're looking at the periodic table, okay? If you think about this, as you move across, the electronegativity is increasing. So anything that's negative, you'd want it more on the F or the O or the N versus the C. Anything that's positive, you want it in the other way. So you want more negative on the right, and you want your atoms to be more positive on the left. What am I saying for that? Meaning these formal charges. These formal charges right here. Now these are all oxygens. But for example, if a negative was on an O and the positive was on a C, that would be what I want. Because I'd want my negative here and my positive here. If it was the other way around and this was negative and that's positive, that's bad. So, but we'll get that into practice. So let's just look at what we're starting with. This is just an introduction to this. So which of the following are related as resonance structures? So let me repeat. Atoms cannot move, only electrons. So the best way to do this is actually to draw out where the electrons are. So now we have a little experience with this. I have the end of a carbon, so I should have 3 hydrogens there, 1 hydrogen here, 1 hydrogen there, and I'm going to have 2 more here because that's a carbocation. Let me look at this one. I would have 3 here, Carbocation, one more bond there, one bond here because of the double bond, and then 1, 2, 3, 4 in the end. Look at my pink bonds. Do they look exactly the same? Yes. No atoms moved. Okay, so because of that, that's a resonance. It's so important. Let's look at the next one. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Carbocation should have 3 bonds total, so 1, 2, 3. Over here, 1. I already had a drawing here. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Take a look. What do you see different? I see 3 here. I see 2 here. Now, I know you could go, well, there's another place. As long as you can find 1. So atoms moved. The hydrogens aren't in the same spot. So because of that, not a resonance. Okay, let's take a look at a few other ones. So again, oh, by the way, just so you understand, like the double bond basically moved and those electrons moved into where the charge was in the same way over here. So that's actually what's happening. We'll talk about that later. Arrows are going to be really important for us moving down the road. Okay, and I will leave that alone for now. So 1, 2, 3, 4. It's a negative, so I need dots. And then 1, 2, 3. Here I'd have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. What do you see? It looks the same to me. So this is a resonance. Okay. Here, this is all that I need to see right here. Just this part. That's the only spot I need to see, right? Here's the H. Here's an H. Here's an H. Now, I get it. I get it. I get it. Look, there's an O and then an OH. The H moved, but if I had to show where it was, that's what I'm seeing. So this is not a resonance. Final one. Is it a resonance? It looks exactly the same to me. Or does it? Well, because that plus, I actually don't need anything there. I can't even write anything. I mean, I could. 1, 2, 3. 1, 2, 1, 2, 3. It's all the same. So that positive actually allows for me not to have an extra bond there. So this is a resonance. And we'll come back and talk about what's favored and what isn't later. Okay? All right, final thing right here is number 2 and 3. It says, which resonance structure is better and would make a more than 50% contribution to the actual hybrid? Why? Bonds or electronegativity. So let's talk about this. Okay, so you have either your double bond or you have charges. So what we didn't highlight yet, and I did this on purpose, was about priorities here. Once again, so right here it said more bonds equals more stable. So the bonds actually, this is a priority rule, meaning that it goes in these orders. So bonds first, then if bonds are equal, electronegativity. So this is about stability. So this is your first real lesson about starting to predict what would exist. So let's take a look at this. I'm going to write this on the side. More bonds, less charges would be the thing I would want. So in this first one, this is clearly the favored. Okay, second one, both have charges, but that has more bonds. So because of that, that's going to be it. So again, reason, more bonds. Remember, charges are the tiebreaker, which we'll get to in a second. But they had the same charges, so I didn't have to deal with that yet. But this third one, I'm laying the table here. Both have bonds, right? I have double bonds, so the bonds are the same. But the charges are in different spots. So this one is on an oxygen. This one is on a carbon. So oxygen, carbon. So remember, the more electronegative should have the charge. Should have, the negative charge. Well, oxygen is more electronegative. So that's why it should be like that. Okay. If this is totally on the side, please just write one more. What if the structure looked like this? Whoops. And I had a positive. And then it looked like this. Because carbons are more positive, you'd want the more positive charge on the less electronegative. We'll talk about that in class. All right. Quickly, final steps, and then we'll let you practice on this and move forward. So draw a resonance structure for the following. So what you want to do is you want to draw the bare bones of it. So the bare bones of this would be basically a Y. This carbon is right here. I didn't move it. Okay. All right. So now what you want to do is you want to move the bond. Okay, that's all you want to do. You move the bond from the bond's location to where the charge is. Okay, so basically this is just my little note. You move bond to charge. But it's got to pivot. It can't just jump usually. So what I would just do is just pivot it to the other side. This is supposed to be a line, I'm sorry. Okay, let's just start over on that. So now the double bond will be on that side. Because of that, this now, it flips. It just basically flips. Other one, same idea. So I have my O's, I have my O, I have my CH3. If I had a negative on this side, and the bond is on that side, I need to now flip it. And that's now my resonance structure. Okay, so now, going back up quickly, let's talk about just one or two of these. Which one's favored? Let's talk about which one's favored for the ones that are resonance. Well, this one has more bonds. I'm going to go from the bottom here than the other one. So that's automatically favored. All right. This one has the same number of bonds, but the negative is on the oxygen, not the carbon. All right. Lastly, this top upper left one, it's neither one's favored. It's the same because the charge is both on a carbon and the same number of bonds. All right, so that is resonance, and we will definitely talk about this in class.